Okay, hello everybody. Welcome back for the Algebraic Geometry Seminar. Um, Today we are kind of continuing our walk through Vakil's section on homology and cohomology. So yesterday we kind of gave an intro to homology and cohomology, and we talked specifically about cohomology as a generalization through right-derived functors of left-exact functors. Um, And so, yeah, today, and then we proved the snake lemma. That was a long thing. Today, we want to go through some exercises and some theorems about long exact sequences and kind of how short exact sequences interact with homology and cohomology. And then, yeah, I don't know. We're just going to see how far we get. um, And if we get through the whole chapter, that's great, but I doubt it, because these are tough exercises. Okay. Goodness, I'm a little under the weather, I think. So yesterday, um, we said an exact sequence can be factored into short exact sequences, um, where we had basically like zero. Well, okay, let me write down the premise. An exact sequence can be factored into exact sequences by zero to cur fi to ai to cur fi plus 1 to 0. And this was the picture that we showed yesterday. If it'll let me button like this. Then this is the ith cohomology group, and then on the left is the ith homology group.
Yeah.
And then we said that for complexes, and I don't think I wrote that down, but I hope I said it. Um, we can factor into this form. We're basically recalling that a complex is where the G composed with F, G F is 0. Um, if we just have that, then we can factor into this. Um, and then, yeah. Yeah, same thing for, so basically switching, dualizing this in from a cochain to a chain, um, just with the standard Hom functor, basically takes cohomology groups and makes them into homology groups.
Mhm.
Um, and so, yeah, if, I guess if A dot is a complex, then we can factor into um, 0 kerf into AI into M Fi into 0 and 0 M Fi minus 1 into cur Fi into the ith cohomology group of the chain complex into 0. And so basically, the next exercise is to describe certain exact sequences, which are kind of like the dual of these two exact sequences here for a complex. And so they say describe exact sequences as follows. And so just kind of noting the similarities between these things. It does actually have a remark that these are somehow dual to the stuff in blue. In fact, in some mirror universe, this might have been given the standard definition of homology. Um, and I'm not really sure what they mean when they say describe.
Yeah.
They maybe mean like put in the morphisms, right? So like F and G and F prime and G prime. Yeah, that must be what they mean. So we are given that G composed with F is equal to 0. And then we are also given, we want to construct, F comma G with cur G equal to M F. And then the same holds for F prime and G prime. So I guess we can start. So the image of F injects itself into A. So the kernel of G has to be like, hold on. So this is the image of F, right? That makes no sense because it's Fi. There we go. And then this is fi minus 1. Or is it? No, it's just So in our regular chain complex, we know that if the image of this F within A overlaps with the kernel of G, then it's everything in A, I plus 1, they get sent to 0 in Coker. Well, Coker of Fi is equal to the codomain of Fi, which is AI plus 1 mod MFI. And so then this is literally just the definition. Oh, that makes a lot of sense. Okay. So, okay, I guess, right, by fundamental homomorphism theorem, at least for modules, right?
Yeah.
Then
Oh.
Cur G is equal to MFI.
Hmm.
And then Fi through F is an injection
Right.
into AI because that is, or into AI plus 1 because that is the next image of it, or at least most of it.
Yeah.
And so then Cur G is the image of Fi. And then
Right.
we just need to show that there's a one-to-one correspondence here.
Okay, that
Um,
makes a lot of sense.
yeah.
I will
Like
say this though.
as long as that
The
is an injection and it's just
Mhm.
embedding, then like it's an exact sequence.
Yeah.
But how do we construct F as an injection? Is it just that F?
Well, is it something that we want to see that cur G is equal to 0? And we use G composed of F equal to 0?
Oh, we really actually. Oh, that's totally it. That cur F is 0.
Or
You
F,
were
my bad.
yeah. If cur F equals 0, then we're done with this sequence. So how do we show that cur F is equal to 0? Well, it's all the things in the image of Fi that go to 0 in AI. Um, or in AI plus 1. Well, we know that this map H has kernel of everything. Um, mm, oh, it's because F is a monomorphism. So we have that HF, if we could get here by some other way, H prime equals H prime F. Well, H and H prime from the 0 map um, have to be the same because they're on the same open, or like the same
Yeah.
hand waving here. I think that works.
Well, is the property of a monomorphism injectivity?
Um, Not necessarily, but I think in the category of modules, yes. Let me
Okay.
Google it. Let me Google that.
Yeah.
Is a monomorphism
Because even if not, I
in
feel like it would be pretty trivial from here.
Yes, it is an injective map.
Perfect.
Okay, so monomorphism is injective. Injective is kernel 0. So cool. So G is exactly the morphism with kernel image of Fi. And then the image of F is exactly the one with the image of Fi. Um, as an inclusion map into AI plus 1. Yeah.
Well, then co-kernel will be AI plus 1 mod current kernel of G.
No,
No?
no, it's co-cur of Fi.
Oh, co-curve FI. I'm sorry. Yeah.
Yeah. You're good. That's a reasonable thing. Um, and then let's go for the second one. Um, so here we have co-cur of Fi plus 1, which is equal to AI mod the image of Fi minus 1. Um, and of course this injects into AI, or I guess it's maybe not an injection. It definitely maps into AI. And then the image of Fi maps into AI.
No, I feel if we do a little bit
No,
of diagram chasing.
nope. Image of Fi maps into AI plus 1.
Oh, all right.
There we go.
We'll
So
leave
this
it now.
happens by Fi.
Okay.
So we want to show that we can construct a G prime whose kernel is the image of F prime. And the image of F prime has cur F prime equal to image of F. No. Nope. Yeah? Yeah, it does.
Yeah, that looks right.
Um, which makes it Fi minus 1. Well, so what is the homology group? The ith homology group is the kernel of fi mod the image of fi I minus 1.
Well, that's kernel of f prime image of fi minus 1.
I'm not sure. Hold on. Let me think through that. You're probably right, but let me think through that. So f prime is the map from the kernel of fi into AI?
No,
Which
I
is
was just saying that the kernel of f prime is the image of fi minus 1. So that homology group is the kernel of fi mod the kernel of f prime. And then the co-kernel is AI.
That's a great note. Fi mod the image of f prime.
No, it would be the kernel of f prime.
Oh. Hmm. Hmm. Okay, so the kernel of fi lives in AI. Yeah, the kernel of fi lives in AI. So then f
Right.
prime is an inclusion map into AI. Um, and since they both have the same mod, it should just be a subset of the co-kernel.
Yeah.
And then
Yeah,
we
that makes
want G prime to have kernel, which is the image of f prime.
Wait,
But the image of f prime is
hang on. If you were to mod out the same thing from both groups, wouldn't that leave them equivalent?
no,
Okay. Oh, you're right.
it's the kernel of fi.
No, you're right.
And that's the other thing is that fi itself moves into a I plus one.
Oh, okay.
Yeah, so it's because it's the kernel of fi.
Yeah.
Let's see. So G prime should have kernel image of f prime. F prime has image, which is basically like an inclusion map into AI. So
Okay.
G prime should have kernel GI is equal to kernel FI. So G prime has cur G prime is equal to cur FI.
Well, then now it's the kernel. So the homology group is now kernel of G prime mod the kernel of F prime.
No. Yes?
Yeah.
Yes. The homology group is the kernel of G prime mod the kernel of F prime. I don't know if that's right, but it seems right.
I mean, I'm just substituting the cur Fi for cur G prime right there.
Yeah. Yeah. That seems right to me.
Yeah.
Where F prime and G prime are the natural inclusions in co-occurring the image of Fi.
Yeah.
And this is like kind of a natural definition of homology.
I'm sorry, Tim, you cut out there. You mind saying that again?
No, I was just saying that it's very natural and kind of
Okay.
elegant. Yeah. Okay. I'm pretty happy with that. Um, so the next section has to do with the dimension of homology groups.
Okay.
And so the dimension of a homology group is essentially the number of I-dimensional holes that the chain complex has. If you can endow it with a topology, then the word hole makes sense. And if you can't, then just think of it as the homology, like as the Betty number.
Okay. You mind
Um,
writing that out?
yeah, yeah. So, definition. Suppose the sequence 0 by D0 into A1 by D1 into A2 by D2 dot 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 D n minus 1 into AN into Dn into 0 um, is a complex of finite dimensional K vector spaces. And we're going to call this complex A dot. We define lowercase h to the I of A dot. And I'll lay this down actually. To be equal to the dimension of the ith homology group of the chain complex. And then the exercise is show that the alternating sum of the dimension of AIs is equal to the alternating sum of HIs. And then as a hint, if the complex is exact, then the sum -1 to I dim A I equals 0. And so I don't know enough about cohomology to say this confidently, but I've definitely seen that this is how you compute it sometimes.
Okay.
Or sorry, cohomology.
Yeah.
So yeah, so each AI is a finite dimensional k-vector space. And this is probably going to be an induction proof, and I hate induction proofs. So let's do an example.
Okay.
I think an example will be worth a lot of money.
Yeah.
Let's do an example with an exact sequence. Oops. Let's see. Maybe 0 into Rn into Rn plus 1 into Rn into 0 with F and G such that maybe F is the map, which is just an inclusion map. And then G from Rn plus 1 into Rn is the projection map with cur G equal to Rn. Oh, except that should be R. And now it's an exact sequence. Oh, and that works out. Hold on. So the complex is exact. The sum -1 to the I dimension AI. Well, this is A1. They start the index at 1. This is A2. This is A3. So this is equal to -1 to the 1 times the dimension of this vector space, which is n, plus 1 times n plus 1 minus 1. Oh, that's so cool. Is equal to n minus n plus 1 minus 1 is equal to 0. Okay, like that's pretty cool.
That
That's
just works out like that.
That's pretty cool.
Yeah.
That's like pretty freaking awesome.
Yeah. That's like the proof of integration by parts. You ever do that one?
I'm sure I did at some point.
You
My
start out with you do the product rule, write out that stuff, integrate both sides, and it just turns into integration by parts.
Yeah, my
So
couch two
nice.
class was a fever dream. It was an 8 a.m.
Mm,
And I lived all the way on East Campus, so I had to walk like a mile.
yeah,
It was like I don't
that's
think I
rough.
should after a certain point, which is
Huh,
very unfortunate because I'm good friends with the professor,
yeah.
um, who I had like way back when. But yeah, okay. Wow, so that really just does work.
Yeah.
That's so cool. That's like,
Yeah.
mm, that's incredible. So then, okay, in short exact sequences, the dimension of this middle thing, or I guess I'll make this a remark. In short exact sequences, the dimension of AI is equal to the dimension of AI minus one plus the dimension of AI plus one. Is that true? I think that's true.
It seems like it would be true.
Yeah, I think it is. So, okay, let's go back to trying to prove this thing though. So, okay, I feel a little overwhelmed by the question.
Mm,
But you know what? Maybe we just have to expand some things. So the sum, so proof, sum -1 to the I of h I a dot is equal to the sum -1 to the I of the dimension of h to the I of a dot, which is equal to the sum -1 to the I of the dimension of uh, d I dimension of the curve di mod m di minus 1. Is that, yeah, kernel of d2, image of d1, yeah. Um, and then that is a module, I think. Surely.
I'd assume so.
Let's think about it. Well,
Well, is the kernel of DI and the image of DI minus one not the homology group?
no, it is the homology group. That's the point. But
Yeah.
this is equal to the sum -1 to the I of the dimension of hold on, I need to check this, but I think it's the dimension of the kernel minus the dimension of the image is dim cur di mod md I minus 1 equal to the dimension of cur di minus the dimension of m di minus 1. Yes, it is. I am so smart. I am so smart. When they talk about smart people, they tell me about me. Maybe the greatest smart person ever. No. Dim cur di minus dim mdi minus 1. And because this splits over sums, this is equal to the sum minus 1 to the I of dim cur di minus the sum, plus the sum minus 1 to the I plus 1 of dim.
Would it be plus?
Yeah.
Oh, you're right.
This is where it all comes through. And so then this is where it's that in short exact sequences, this becomes 0.
Yeah, we just have to show that cur di is equal to image of di minus 1. Because
So
they'll
really,
just cancel each other out because
we want to
I mean,
show that this is equal to the dimension of the ith vector space. Well, the dimension of the ith vector space by rank nullity theorem.
geez, we're going way back for that.
Yeah.
Huh.
So the dimension for V is equal to, assuming V has an injective map,
Mm-hmm.
is equal to the rank of the image to MDI. Or no. Rank nullity adjacent. My linear algebra teacher is probably looking down on me and Jim right now. The dimension of the kernel of DI plus the dimension of the image of DI minus 1. And I guess this would be dim AI. And so we really just want to re-index this thing on the right. We want to re-index this so that we can get this thing plus this thing.
Yeah.
Well, we can move out and I. Like we can move out a -1. Is it? Is it? What is the thing that we're trying to prove? We're trying to prove. Oh, this needs to be a -1 to the I. I feel like we might be overcomplicating this. Maybe this is equal. Like if we start from here, this is equal to -1 to the I. I don't know how to get from there.
Tim, to get to 0, if we show that the dimensions of the
But we're
kernel
not
of
trying to get to
DI,
0. We're trying to show that that was like a sub point of it. We're trying to show that it's this. The
oh,
zero
okay.
one is easy. The 0, 1 comes from the fact that the homology group of a short exact sequence is 0.
Oh, okay.
Um, but showing that let's see, let's follow this math through. Maybe it was meant to go in a forward direction. Maybe it was meant to start with the left-hand side and get to the right-hand side.
Hmm.
Let's try that real quick.
Yeah.
Switch. So we want to start with -1 to the I of dim AI. I think that's correct. Well, this is equal to the sum -1 to the I of the dimension of the kernel and the amorphous pink blob. And so this is equal to the dimension the linearity thing is killing me. That's the thing that sucks is
Yeah.
I need this to be a plus. Or I need this to be a minus,
Hmm.
but it's a plus, and I don't know what to do with that. Let me check Google.
If you were to distribute out the -1 to the I, to both,
Oh, and get like
and then pull the -1 out from there.
-1 to the I -1 minus Jim. I just don't think that works.
What if you did minus 1 to the I times dim cur to the I minus negative 1 to the I minus 1 dimension? I'm just kind of spitballing here at this point.
No, I mean that's what we need. So I minus one, or maybe it's just. Hold on, I might have come up with a trick.
Yeah.
Then this is equal to the dimension of the ith homologic group, and that's why it's like that.
Yeah.
Is equal to the sum minus one to the I dim for di mod m di minus one. There we go. Is equal to the sum minus one to the I of hi of a. Boom. Okay, that's it.
You mind going back down real quick?
Yeah, that was very satisfying.
Perfect.
Cool. That's pretty awesome.
Yeah.
That felt very satisfying.
Yeah. Once we figured it out.
Dude, I was telling I was hanging out with one of my like high school friends last night from
Yeah.
way ago, like my best friend. And he was like, we were talking about like, the different things we do professionally now, and I was
Mhm.
like, yeah, I just kind of feel like, because we were talking about like how Fortnite had been so popular, and I was like,
Right.
yeah, like it kind of feels like math is just like peak Fortnite. And he was like, dude, you're what? Um, okay, important exercise. Wow, there's like so many of those back to back. Um, we have not even made like a half of a page of progress. Wow.
Oh, there we
Um,
go.
although I will say some of the stuff that we get to right after this was covered yesterday, so that's fine.
Oh, perfect.
Um, okay, so I'm going to say this is a theorem and we're going to prove it. Let script C be an abelian category. Define the category of complexes over C.
Uh,
Uh,
what's the word after category?
of complexes.
Huh? No, 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 no. The first category after
Oh,
abelian category.
define. Sorry.
What are we defining? I'm sorry.
Com C
C.
to be the category of complexes over C. Yeah, I'm sorry.
Comma.
My handwriting is not great. So OBC or OBCOM consists of sequences, or sorry, infinite complexes. Um, A I minus 1 to F I minus 1 into AI into AI plus 1 Fi plus 1 um in the category C, and the morphisms of com are more from complex to complex in the manner of show that com is an abelian category, or rather, since we stated this as a theorem, I'll say com is an abelian category. Um, so he says that this is important, and I'm sure it is, but that's so many things. Okay, so we want to show that morphisms form abelian groups. We want to show that we have a zero complex. We want to show that we have products of two complexes. We want to show that every morphism has a kernel and a co-kernel. Every monomorphism is the kernel of its co-kernel, and every epimorphism is the co-kernel of its kernel.
Lovely.
Most of these are actually pretty easy. Like this is commutative by the definition of like a commutative diagram.
Yeah.
Form an abelian group, such that the composition of morphisms distributes over addition. So like more A plus B into oh no. Okay, no, we actually do have to do this. Damn. Damn.
This a new
It's
base change diagram of pain and suffering?
it's not even a base change that like it's not actually that bad. It's just that like the snake lemma was like a new base change diagram of pain and suffering. Um
Well, that was just diagram chasing.
I mean, in a way, so was the base change diagram of
That's
pain and
fair.
suffering. It was a particularly nasty one, but like,
Yeah.
okay, so now we want C and H and C and H and C and H. And we want morphisms down because we want to show that more A comma B plus more B comma C is equal to more A comma C. And then we also want to show that it's an abelian group, but that actually kind of works itself out. And this statement is clear because we can pretty clearly define this as the composition of the two maps down.
Yeah.
Like I think that this just kind of holds.
Right.
And since that holds for everything, then like we're fine. And then the zero object, zero in com, is the zero complex, 0 into 0 into 0 into. Right.
Yeah.
That is not written very well, but like if I move some things around, really this is what we mean. Right. And then it has the product of two objects. This is where we might get the base change diagram of pain and suffering. Yeah. Let me copy the whole thing over. So if we have A defined like so, then the product of complexes should have the unique factorization through some product. And I think this is maybe just the union of complexes.
Mm.
I'm not really sure how to define this.
Yeah.
I'm actually very not sure how to define the product of complexes. Let me Google it.
Okay.
Product of complexes. Homological algebra. It's a cup product. That's not. What is a double complex? What? A double complex is a general chain complex. Oh, it's the same thing. It's literally just drawing the arrows down. That's awesome. Okay. I love when the words actually mean what they're supposed to mean, like etymologically, because it's just awesome. And
Yeah.
it's actually more that there's a hypothetical arrow that either goes to zero. And in terms of long exact sequences, we can just write this as just like this. Um, and then, okay, now for the tougher stuff. Now we need to show that every map has a kernel and a co-kernel. I think this is pretty obvious. We're defining it on a category that is an abelian category,
Mhm.
and every complex is a map between objects in the subcategory. I think that like that's where most of the abelian stuff comes from.
Yeah.
It's just like, hey, look, subcategory is abelian, and it inherits like all of its properties through maybe the product. I don't know. Um, I don't know. I don't feel like this is like I don't know. 15.6.5. What? 15? Wait, 1.5.6.5 induces a map of homology. Ah, yeah. I'm willing to call it a day here. Um, and abelian stuff can basically prove itself. So abelianness is inherited on script C. Um, so theorem, this double complex induces a map of homology. From the ith homology group of A to the ith homology group of B. Furthermore, HI is a covariant functor from com C to C. I can see how this would. So, okay. So I guess first consider Or I guess no, we start with just this. With F, G, and H. Then the homology on A at I comes from then HI on the A complex is equal to the kernel of G mod the image of F, and the homology group on B is the kernel of H mod the image of G. Is this making sense?
Yes.
And so then the map of homology, so HI on the A complex to HI on the B complex is a map that sends G mod MF to H mod MG. Oh. Yeah, oh no, that is the right way to think about it. But the homology, oops. The ith, this isn't the ith homology group. Within this, we have to pick out, oh, fucking hell. It's not, this is wrong. This is wrong. This is actually very wrong. If this were our complex in long exact sequences, then yes, that would be the homology. However, the ith homology group of the AI complex is the kernel of Fi mod the image of Fi minus 1, and then the kernel of Gi mod the image of Gi minus 1. And so the map of homology groups maps the kernel of Fi mod the image of Fi minus 1 to its counterpart in the double complex. And that makes a lot of sense. In terms of HI being a covariant functor from the category of complexes to its underlying abelian category, HI gives us something that is definitely in OBC. And then morphisms between HI, or HI of oh yeah, this is in Morse. So HI is a covariant functor. Does that make sense?
Yes.
Okay. Okay, that's interesting. So, as a theorem, but not an exercise, homotopic maps, which I'll define in a second, induce the same maps on homology. And as a definition, two maps of complexes F from C complex to D complex and G from C complex to D complex are homotopic if and only if there exists a sequence of maps W from CI to DI to DI minus 1 such that F minus G is equal to DW plus WD. Where D is what? Hold on. Homotopy on complexes. Homotopy on complexes. Ah, okay. Here we go. So it's WI minus 1. Hold on, I don't like his definition. Google has a much better one. WI minus 1. Wait. Hold on increasing complexes. Okay, and now there's not a definition. Hold on. Okay, I'm just gonna have to dualize this. It's that. So in a decreasing complex, here we're going I to I minus 1. Then this should be WI. WI such that FI minus GI is equal to WI WI minus 1. And then EI and DI minus 1. where DI is the ith map. What? Okay, so this is what I'm confused on. Is what the hell? So like I understand where DI comes in.
Hmm.
Um, what is the boundary map? It's the ith boundary map. Oh. This is the A ith map. And this is the B. No, sorry, this is the C ith boundary map, and this is the D ith boundary map. So this is I minus 1th boundary map. D, so this is going like di minus 1, di minus 1, di. This is going ith boundary map. And C, CI, DI, CI plus 1. Cool. Okay. So, fun fact, if you need to Google this later, you can't because Google has it going for homological chain complexes, not co-chain complexes.
Okay.
So this whole time, I will add we've been working with cochains without really saying that.
Mm-hmm.
So a cochain is just us taking the Hom functor and then doing like an arrow reversing thing.
Yeah.
And so like when we reorder things, usually sequences for homological algebra go decreasing. Um,
Mm-hmm.
we're working with them increasing, and that's cohomology. And so we're doing cohomological algebra.
Yeah.
And so all of the definitions that are on Google are not very helpful. Um, and so
All
then
right.
now we want to show, okay, so the theorem, um, now we want to prove this theorem. And I'm just going to move the theorem down here. Okay. So, two maps are homotopic. Okay, let's just bring the double complex down. So we want C to go to D. And if they're homotopic, then we have something, oh, and I need to replace everything with CI minus 1, CI minus 1, D. And then we're gonna have like a little W Ci to di minus 1. And this is wi. Wi. Oops, I keep doing that. And then fi minus gi. Bro. What? Understanding this definition is like a headache. And the thing that sucks is I know that this is going to show up in the algebraic topology seminar later. So I know it's going to be like important. Homotopy of complexes. So we want wi. We are given that they're homotopic. So then fi minus gi. Fi minus gi is equal to di minus 1, which is gi minus 1, wi on the right. That makes sense. Plus wi plus 1 gi. And just visually, oh, except it's not gi, it's fi.
And is it wi plus 1 or wi minus 1?
It is wi plus 1. I think. Nope, minus 1. Good catch. Fi and wait, that doesn't make sense. Wi and gi minus 1 makes sense. Wi plus 1 makes sense with fi. Because if it were fi minus 1, then that makes no sense.
Yeah.
Or this whole thing has been written backwards. Wait, hold on. The di minus 1, gi minus 1, wi, and then the wi minus 1 and c. It would have to be ci minus 2. So I think that it might be easier to use wi plus 1, and I don't think we're doing anything terribly wrong. Because now we have wi plus 1 and fi. I'm gonna run with it, and if it becomes like really horribly blatantly wrong, then we'll fix it when we get there.
Mm-hmm.
But I think that this looks right. Like there's that, and then there's that. And I think that that's what should make sense. And since I got this definition from chain complexes on Google, I'm going to say that my mathematical intuition beats Google AI summary of Math Stack Exchange.
All right.
Talk about a rock, paper, scissors contest. So Fi minus Gi. So let's first note Gi minus 1 Wi goes from Ci to Di minus 1 to Di. And Wi plus 1 Fi goes from Ci to Ci plus 1 to Di. And so that's why we can subtract or add these two things. Okay. 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 All right, this is making sense. This is like the definition is starting to make sense. Usually around this point in the lecture, I start thinking about like what I'm going to title this lecture on YouTube based off of what we've covered, and dude, I don't know. Probably something about this homotopy on consequences. So now we want to say that they induce the same map on homology. So we know we have a covariant functor into the subcategory. So we want to say that in terms of homology, hi of c dot into hi of d dot is defined by and this is where it's all going to get bad. I'm just going to do it for this middle thing here.
Okay.
That's what we're looking at. Cur Fi mod m Fi minus 1. And we really need this to go through something like this. So we need this to scoot over a little bit. And then cur Fi plus 1 mod m Fi. And then at the same time, we want cur Gi mod m Fi minus 1 cur Gi plus 1 into m Fi. That can go forever. That can go on forever. Just going to move these apart a little bit so that we have space for everything. And then I also need cur Gi minus 1 mod m, and that's not mod mf. That is so not mod mf. Gi minus 2. And so then we're hoping for induced maps. So, okay, we have our straight down arrows that are induced by homology. Um, um, one second. Um, I guess I'll just call it HI. Oh, it doesn't have a name. That's fine. But now we need HI of WI. So we need HI of the map. That'll be WI plus 1. That'll be W, or the homology functor of WI. And so what we want to show, and I guess, hold on, let me write this out as this induces, like, so we want to show that if this is HI of Fi minus 1, and this is HI of Fi, and this is HI of F I minus 2, no, of Gi minus 1. This is HI of Gi, that HI of Fi minus HI of Gi is equal to HI of Gi minus 1 Wi minus HI of Wi plus 1 Fi. I'm not really sure how to do that. And we're pretty much out of time. So I'm going to say that we'll start off tomorrow's lecture with this.
Go down
We
for
made it.
just a second.
Huh?
You mind going down for just a second so I can like finish it?
Yeah.
Thank you.
Go ahead, think about it, over the next day. See if you can come up with like a proof.
Yeah.
But yeah, otherwise we'll open up tomorrow with it. And yeah, we got through about a page today, which is pretty good.
Yeah.
Especially for this section. I'm thinking our Christmas present will be that we will have finished the section on homological algebra by then.
Huh.
maybe.
All right.
So anyway, cool. Have a great day. Let me stop the recording. And yeah.